In this video, we're going to cover section 1.1, Introduction to Kinetics. Kinetics can be subdivided into two areas, chemical kinetics and physical kinetics. Now, the majority of this course will focus on chemical kinetics, but we will also discuss aspects of physical kinetics. So chemical kinetics, this involves the study of the rates and mechanisms of chemical reactions. It examines the evolution of a system towards an equilibrium with respect to chemical composition. Now, the rate of a chemical reaction may also depend on controllable variables, such as the temperature, the pressure, and the presence of a catalyst. So as a result, the rate of a reaction may be optimized by choosing appropriate conditions. Physical kinetics, on the other hand, involves the study of transport phenomena, such as diffusion and viscosity. It examines the evolution of a system's physical properties as the system relaxes towards equilibrium, but without any change in chemical composition. So the question we should ask ourselves is, what happens in a chemical reaction during the period between the initial state and the final state? How do reactants become products? When you think back to Chem 250 in thermodynamics, what you were mostly concerned with was conditions surrounding the initial state and conditions surrounding the final state. For example, looking at the free energy of those two states and comparing that difference. In kinetics, what we're interested in is the pathway from one state to another. So we want to know more about how does a reaction proceed from the reactant state to the final product state. So as you can see from this figure, the potential energy can be plotted against a particular reaction coordinate. This is the pathway that those reactants will take towards the formation of new products. And we can capture the change in the energetics of the system as we go from left to right. And we'll talk about characteristics such as the activation energy, which we know is that barrier to product formation, the energy required for this reaction to be successful, the energy required to overcome this particular barrier, which leads up to that transition state complex, and then finally leads to product formation. In chemical kinetics, these questions are answered by determining the timescale and mechanism of a chemical reaction. Thermodynamic descriptions of chemical reactions, they include the Gibbs energy for a reaction and the corresponding equilibrium constant. Now, these quantities can predict the reactant and product concentrations at equilibrium, but they are of little use in determining the time scale over which the reaction occurs. Thermodynamics may consider a reaction spontaneous or non-spontaneous, but it doesn't give you a sense of the time scale, whether or not that reaction occurs over a very short time period or a very long time period. Does the reaction occur on the order of femto-pico nanoseconds, or is this a reaction that'll take hours or days? So chemical kinetics can provide answers to these questions, both the time scale of the reaction and the mechanistic details of that chemical reaction. Now, during a chemical reaction, concentrations will change with time as reactants become products. So as the reaction proceeds, we will expect to observe a decrease in reactant concentration with a corresponding or concomitant increase in the product concentration. And that's shown in this figure below, that if we were to follow the concentration of a reactant over a period of time, as it decays from its initial concentration to some lower concentration, we would expect a concomitant increase in the product concentration. And if this reaction was from a single reactant to a single product through a single transition state, we would expect a profile like this, where we have almost a mirror image between the decay curve and the growth curve, if you will, for the formation of that product. Now, one way to describe this process is to define the rate of change of the concentration of a species with time, a quantity that is referred to as a reaction rate. So the central idea behind chemical kinetics is really this. By monitoring the rate at which chemical reactions occur and determining the dependence of this rate on parameters like temperature and pressure, we can gain valuable insight into the mechanism of the reaction. Now, experimental chemical kinetics also includes the development of techniques that allow for the study of chemical reactions. And those are always being pushed further and further so that we can understand more and more about reaction mechanism. In addition, theoretical work has been shown to help significantly with our understanding of reaction mechanisms and the underlying physics that govern the rates of chemical transformations. It really is a synergy between experiment and theoretical chemical kinetics that has provided for dramatic advances in this field. Chemical kinetics has literally application in every area of chemistry and biochemistry, such as catalysis, materials processing, and atmospheric chemistry, to name a few. So over the course of this semester, we will examine the rates of chemical reactions and how they are measured using various spectroscopic methods. And I hope to be able to demonstrate to you how these studies lead to an understanding of reaction mechanism for these various chemical processes. So if you have any questions about our introduction to chemical kinetics, by all means, send me an email. Thank you.